Hi, so today I'll discuss some uh, questions from week 7 and topics that were discussed in week 7, where we continued some things about uh, the duality in LPs. So, if you have an LP P and its dual LP D, then we have that if P is like you can say if either P or D are unbounded, then the other is infeasible. And the other point is if either has a finite optimal value, then so does the other, and they are equal. This was the duality theorem of LP. Then what to discuss is the Farkash's lemma. Okay. It said basically uh, exactly one of the following is true. That is, there exists x such that ax less than 0 and cos x less than 0, or there exists y such that A transpose y is equal to minus c and y greater than equal to 0. It is also called theorem of alternatives. Okay, and this the proof of this was discussed via the duality, by using the duality of LP. The thing that was discussed was max flow min cut theorem. In that, I think in last class I had shown the max flow problem. So you have a network and discard this. So basically you have some source, and you have some intermediate nodes. This is your okay. This is your target. This is the source, and each of the nodes has some capacity. Some capacity. Okay. I think what notations are used was cap ij. I'm using a different notation, that is uij, upper bound on the capacity. Okay, so flowing from, let's say this was I, this was j, then the flow from I to j as an upper bound uij, lower bound lij, flow from I to j. Okay, and you want to maximize the flow from the source to target with these constraints. So then what you get is this L. Let me reduce its size. So you get this LP, and these constraints are called balancing flow constraints, which is basically the inflow to any node should be equal to the outflow from the node. Okay, so this is the max flow LP. You want to find maximum flow that can pass through from source to target given the capacity constraints of each of the edges or links from each of the nodes. And what was shown was the dual of this LP. Dual LP, you get some dual LP is the min cut LP. What the min cut LP does is, so you get a different LP, the dual of this, and that LP gives you the min cut. What is a min cut is, given a network, the same network, whatever is there over, it finds a cut separating the source and target such that the edges that it cuts and the sum of its capacities should be minimized. That is the min cut LP. Okay, the sum of the flow that goes through it should be minimized. Now why does it, so the property of the LP and its dual LP is its optimal value is equal. So how does the min cut LP is a optimal value, that is the cut which minimizes the weights on the edges, equal to the max flow LP solution. So how that happens is, when you find the min cut, so when you solve the min cut LP, when you find the min cut, what happens is you find a cut which selects the edges which is the bottleneck in your max flow. So those edges are selected which happen to be the bottleneck, which decide how much flow can go through. So if you have some big network, and if there is one single edge, in this source, this is your target. If a network was like this, then your min cut will find this, because this is the bottleneck. You have to pass through this to go to your target, and this will be, by default this will be the min cut, because you have, that is the only connecting path from source to target, and subset is also the bottleneck. Okay, so you're restricted by how much you can pass through this link. So that is what min cut does. So you can only pass through this, like the max flow that can go from source to target is the maximum value that can pass through this link. Okay, so that's how intuitively the main cut results in the max flow solution. And the other thing that was discussed was the shortest path problem. And shortest path problem, that was basically you have some network, and you need to find the shortest path, and each edge has some value which may be equivalent to the distance from that path to from I to j, distance from I to j, you can say from Cij, or cost of going from I to j. So you want to find the shortest path which minimizes the cost from some source to target. Let's say so you need to find some path which has by selecting edges which minimize the cost, ch. This was the shortest path problem, and its formulation was discussed. Then a different form of Arcus lemma was discussed. So there are many formulations of Farkash's lemma. If you just Google Farkas lemma and Wikipedia page, you will find a bunch of different formulations for Farkas lemma. The other thing that was discussed was the complementarity slackness. So what it basically said is if you have some LP like this, beta equals 100. So this is your primal, this is your dual, then the complementarity slackness theorem, what it says is x star in the feasible region of primal is optimal if and only if there exists lambda star in the feasible region of dual, such that summation aj to x star j less than b implies lambda I star equal to 0. So you have as many dual variables as many you have these primal inequality constraints, and you have as many uh, primal variables as many you have dual inequality constraints of this form A transpose lambda. So wherever so for your x star solution, wherever this inequality constraint of ax less than equal to b, wherever it is strict, the dual variable corresponding to that should be equal to 0. And the same thing holds for the primal also. So wherever lambda star aij equal to 1 to is greater than cj implies xj star is equal to 0. So wherever this is c, wherever this inequality is strict, this is 0. And wherever, you can also say wherever summation lambda star aij is equal to cj, that can imply like xj star is greater than equal to 0. Similarly, if aij xj star is equal to bi, that will imply lambda star is greater than equal to 0. Okay. So if x star j is greater than 0, that implies summation lambda star aij is equal to cj. Similarly, if lambda j star is greater than 0, that implies summation aij xj star is equal to va. So this is the complementarity slackness theorem. So this was what mostly discussed in the week 7. So let us do one problem. Okay. So we have to say whether this is true or false. True or false. Mm, Only one of one and I can say yes, true. So one is saying AI greater than 0, 2 is y transpose A equal to 0, y equal to 0, y not. So what they are saying is at a given time only one of the statements can be true. That is similar to what we had in Farkash's lemma. So what we had in Farkash's lemma was uh, we had this thing, right? This was Farkash's lemma for us. Okay. So what I can consider is Farkash's lemma with let c equal to 0, right? So what I need to show is if If Ax greater than 0, then for some x, then 2 doesn't hold. Okay. So we know Farkas's lemma. So how do we prove it using Farkas's lemma? If I hold let c equal to 0, then I have 1 tells me that I let c equal to 0. 1 says there exists x is that ax less than equal to 0. Okay. So let me go with the first statement. Okay, this pen is a little bit acting a little slow for some reason. We turn off some of the apps. So let me go with the first statement. It says ax is greater than 0, which implies let me go do it. There exists x such that ax greater than 0, which implies ax is greater than equal to 0. So which also implies a of minus x is less than equal to 0. Okay. So a of minus x is less than equal to 0. That implies this implies 2 won't hold. And 2 is saying A transpose y equal to 0 and y equal to 0. Okay. So we showed that if 1 is true, then 2 is not true via Farkas lemma. Via Farkas lemma. Now we need to show that if 2 holds, then 1 doesn't hold. Okay, so 2 says y transpose this is equal to 0. Like 2 says there exists y such that A transpose y equal to 0 and y greater than 0 equal to 0 and y is not equal to 0. So this implies my A transpose y and y is greater than equal to 0, which implies 1 doesn't hold via Farkas lemma. 1 doesn't hold means no x such that ax is less than equal to 0. Okay. So there is no minus x also, which also implies no x such that ax greater than equal to 0, because then a minus x is less than equal to 0. Okay, so we have shown, so if ax greater than equal to 0 doesn't a minus x like ax greater than equal to 0 doesn't exist, means this implies ax greater than equal to 0 also doesn't exist. Okay, if ax greater than equal to 0 doesn't exist, then that means ax greater than equal to 0 doesn't also doesn't. So we have shown if the Roman 2 doesn't exist, then Roman 1 doesn't exist. And sorry, if Roman 2 exists, then Roman 1 doesn't exist. And the first part we showed was if Roman 1 exists, then Roman 2 doesn't exist. If 1 exists, then 2 won't hold. So via Farkas lemma, that is Roman 1 doesn't hold. Sorry, Roman 2. This is Roman 2, right? Second part was we started with Roman 2 and we showed that this one doesn't hold. So Roman 1 doesn't hold. So we used Farkas lemma to show that if a is greater than equal to 0, then this won't hold. And if second is true, then 1 doesn't hold. Because we know Farkas lemma is true. Okay. Similarly, you can try a different example. And if you're not able to do that, then you can post in the discussion forum. Okay, to show that only. Show only one holds simultaneously. Okay, via the same kind of arguments you can try to show this one. So let me try a different question. Okay, you have this IP such that ax plus I y is equal to b, x greater than equal to 0, y greater than equal to 0. Okay, and b is also greater than equal to 0 is given. So what is the dual of what is p dual of p? So if I have min C transpose x Ax equal to b greater than equal to 0, then its dual is max b transpose y transpose y less than equal to c, right? Right, by dual. So the dual of this, if you see, this is min e transpose y and a x equal to b, and your x and x is greater than equal to 0, y is greater than equal to 0. So this is of this form: minimum C transpose x Ax equal to b, and your variables are greater than or equal. So dual will be dual, let's call it d, will be max. So y is already used, so let's use lambda. So lambda b transpose lambda A transpose y is less than equal to c. So what we will have is A transpose is of this form, right? Whose lambda is less than equal to c is e for us. Okay, so this you can write. Okay, so here you had C transpose x, so it is you can say 0 and E transpose. Sure. Okay. So that means this is 0 and E. Because I have xy variables here, so I need to adjust it accordingly. So this is basically a lambda less than equal to 0. should be A transpose, and I transpose is I only. So A transpose lambda less than equal to 0 and lambda less than equal to E. Okay. So basically if I take transpose of this is what I get. I'll get this. If I take I transpose, that is A transpose I transpose is A transpose I. Okay, that is what I have done here. And 0 E transpose is this 0 E transpose is this 0 E transpose, because I have C here and C transpose X here. Okay, so that's how we have adjusted this part and this part. So that's how we got this. This is basically our new problem. This is the dual. So this question is show primal as a basic feasible solution. So basic feasible solution means we need uh, something of this form, right? X b x n is equal to and this a you have split it as some b n and b n x b x n, this is equal to b. And b inverse b greater than equal to 0. This is for basic feasible solution. So this is our primal. So how can I get a basic feasible solution? It is given to me that b is greater than equal to 0. Okay, and if I substitute x equal to 0 and y equal to b, I get this is equal to b. That is what I want, right? I need some variable 0. And my basic feasible solution should be all positive, and it should, so basically my basic feasible solution should be all positive, and it should correspond to this form. So I have x y equal to 0 comma b. I should write it like this: x y. So a times 0 is 0. I times b is equal to b. So already our matrix is split in this bn form, right? We already have this ai form. I is this, and a is this. Okay, because I is all linearly independent columns, so it's an identity matrix. Linearly independent columns. So 0b is a BFS. Okay, so we have BFS. Now see, now there's a question which is asking, show primal always has an optimal solution. So if we are able to show, we know that primal has one solution. Like this is a basic physical solution, so we know it has a physical solution, but it has an optimal solution means it is not unbounded. So we need to put some bound, and how we can put a bound is if we show that dual is also feasible, right? Because if dual is infeasible, that means primal is unbounded via the theorem of the primal dual theorem. So if dual is feasible, that means the primal is also feasible. Primal is an optimal solution. If dual is unbounded, then primal is infeasible. But we know that primal is feasible via our basic feasible solution. So if uh, so we have primal is feasible. So I just need to show that the dual has a, to show that primal is not unbounded, I need to show that dual has a also has a feasible solution. So what is this feasible solution of the dual? If I put if I keep lambda equal to 0, then what do I get? Okay, one more thing is given is this E is also greater than equal to 0. This I forgot to mention. And E greater than equal to 0. Yeah, that is important information. So if E is greater than equal to 0 means I can substitute lambda equal to 0 here. So 0 is feasible in dual. Lambda equal to 0 is feasible in dual means B transpose 0 is equal to 0 is upper bound of sorry is lower bound of primal, right? Because the primal objective value is always greater than equal to the dual subjective value. Therefore primal is bounded implies optimal solution exists. Okay. So in this case the optimal solution always exists and we are able to show it via the feasible solution of the dual. You can also write the complementarity slackness conditions for this via this lambda and xi. Let me increase the page size. Complementary slackness So what were the complementary slackness conditions? Okay, for this it should be something like hmm, it should be something like if I have ax equal to b, so something like this. So ax less than b, x greater than equal to 0, and a transpose lambda then let's see lambda greater than equal to 0, then I'll have lambda star ax minus b equal to 0, right? X star and A transpose lambda star minus C X star equal to 0, something like this. So in this case we have this constraint AIXY equal to B. So I guess I'll have A transpose lambda star times X star is equal to 0. And it's already AX minus B, right? this also is lambda minus e y star. This is equal to 0. This is from these two constraints. Okay. So this is the complementarity slackness. What we get. Okay, let me try this. If you have x such that ax equal to b, x greater than equal to 0, is not empty if and only if primal value is 0. Prove. So I want to prove that this set is non-empty if and only if primal value is 0. Okay. So this set is non-empty only if primal value is 0. Primal value is 0 means what? So we are saying y equal to 0, ax is equal to b. That means the primal solution is 0. Okay. So x equal to xy equal to x0 implies primal value is 0. And ax is equal to b. So if primal value, we already have a bound on the dual. Okay. And 0 is lower bound of primal value. So that means the primal only if it achieves this lower bound, is this set non-empty, right? Okay, so if I substitute x comma 0 into the primal, I get 0 and I get this ax equal to b, and only if it satisfies that ax equal to b and x greater than equal to 0, it is a solution of my primal. And it is non-empty means the primal objective reaches 0. If and only if primal optimal is 0. And it will be optimal value because it is the lower bound. So it is optimal. Okay. So what we discussed in this question was we have this primal objective given, primal LP. It is given as b greater than equal to e is greater than equal to 0. Here as what is the dual? You see it is kind of in the standard form, so we can convert it. We know the dual of the standard form, so that we wrote here. Then we were asked to show that primal has a basic feasible solution. So for basic feasible solution, we need something of this form where B is a square matrix with linearly independent columns, and B inverse B is greater than equal to 0. So we know here that I is a square matrix identity, and you can substitute 0 and B to get B. So that satisfies the constraint, and it is all positive. So we show that xy equal to 0 b is a BFS. Next, the question is show primal always has an optimal solution. So primal has an optimal solution means we know primal has a non-empty feasible region. So we need to show that it is not unbounded. To show it is not unbounded, we need to show that dual is not like dual is feasible. If dual is feasible, then primal is bounded. So we show dual is feasible by substituting lambda equal to 0. When you substitute lambda equal to 0, we get it solves this. So primal is bounded. Optimal solution exists. Write complementary slackness conditions of primal and dual. So that we wrote via this. Next is this set is non-empty if and only if primal optimal value is 0. If primal value is 0 means it will be optimal because 0 is the lower bound of primal value which we obtained from here. So if we substitute x0, we get this set in the primal, right? and that set will be non-empty, means the primal value is 0, and 0 is lower bound of primal value, so it is optimal. Okay, so only if the primal value is able to achieve 0 will this set be non-empty. If we did not show another direction, we also need to show that if primal value is 0, then this set is non-empty. And that is automatically implied with this, right? So that is it. I think for next week onwards, what I'll try is I'll ask for some questions to be posted in the discussion forum, and I'll try to discuss those questions in the for weekend. If you have any doubts, you directly post in the discussion forum Google group. Okay, yeah, I'll stop the recording.